All right, class, this video is going to cover eigenvalues and eigenvectors. All right, and we are going to concentrate on the 2x2 case in this video, and I'll post the last video for this section, which is going to cover eigenvalues and eigenvectors for 3x3 cases, but I wanted to separate these two because they're the approaches will be a little different. So this will be a 2x2 case. Okay, so the idea here is, let me just give you a scenario if that we're given some matrix A, which again is 2x2. Are we able to can we isolate a scalar row and vector v such that A times this vector v is equal to row times the same vector v. Or in other words, this is equivalent to, let's go ahead and subtract row v from both sides, and we could simplify this further, so it'll be A vector v minus row vector v equals the 0 vector, or just using basic algebra, we can have it that, let's factor the v out, and we'll have the matrix A minus the identity matrix times row dotted with this vector equal to the 0 vector. So what is the intuition here? So the idea here is, let's say we got let's say we have a some vector. I don't know, I'm just going to randomly choose this point here, this vector here. All right, looking at this math, we can take a vector and multiply it by, so hypothetically, we take a vector, multiply it by some vector x, and we get some other vector b. We've seen systems like that before. So in other words, matrix A multiplying vector x changes the direction of vector x into this vector b. All right, or we could think of it as like, if vector x and vector b are the same, then it must be the case that A is the identity matrix. Okay, so we could think of matrix multiplication as changing the directions of your vector, right? And we saw some of those elementary vectors earlier on. They were identity matrices, and they did some simple things to our vectors. But here in the general case, the intuition is that multiplying by a matrix A changes the direction of matrix X. All right. What we're looking for in this case is we're looking for a scalar row and a vector v such that if we multiply A out into this, it doesn't change the direction. All right. And it ends up sending this vector back to the origin, right? It's like the anti-vector. It's like antimatter, all right? So an eigenvector and an eigenvalue work together to kind of bring any vector, you're not going to change its direction, and you're going to collapse it back into the origin like a black hole of some kind, all right? So pretty cool intuition there, pretty powerful stuff, but how do we work with this, all right? So there's a couple of results that come from this. You know, if we take what this tells us here is that let's say if we have a matrix A minus rho times matrix I, I'm sorry, the identity matrix I, and let's say that the columns, so the columns are given by B1, B2, all the way out to Bn. And again, in this case, it's a 2 by 2, so this will just be B1 and B2. But what we're saying is that it must be the case that B1 times eigenvector 1, plus B2 times eigenvector 2 plus ... Bn eigenvector n. Those are all going to be equal to the 0 vector here. And then this has a whole other set of consequences. One is that we're going to use is that it must be the case, if this holds true, if this is one of the rules for our determinants, it must be the case that the determinant of A minus rho I, this determinant has to be equal to 0. So if we can actually solve for the rho, the value rho that makes this happen, we can actually solve for the eigenvalues. Then what we do is we plug that back into this expression and we can isolate the eigenvector. And that's the step that we're going to take. All right? So let's say we've got some 2 by 2 matrix A, and it's just our classic A, B, C, D. All right. We want to solve for this expression here. So we're going to set up A minus rho, and then B, C, and then D minus rho. All right. You can verify that these, this is the determinant version of this matrix here. And this is going to have to be equal to 0. So if you remember what the determinant formula is for a 2 by 2 case, that's just A minus rho times D minus rho minus C times B. B times C is equal to 0. Let's go ahead and factor this out. So this will be AD. I'll start down here. So we're going to have A times D minus A rho minus D rho plus rho squared minus BC equals 0. And, if you kind of take a look at this, what you'll see is that this, we can rewrite this as rho squared, right, minus, we've got a row here and a row there, so it's going to be A plus D times rho plus A times D, so that value here, minus B times C equals 0. All right. You go back to this, you can see that A plus D is something called the trace of a matrix. When you add the diagonal elements, you get the trace. So this will be rho squared minus the trace times rho. And then you can see here AD minus BC is the determinant. So that's going to be plus the determinant equals 0. And that's our formula for the 2 by 2 case. All right. And if you remember, we're going to go back to our elementary school days and we're going to use the quadratic formula. So if you recall what the formula is for this, we've got an A, we've got a B, and we've got a C, set them equal to 0. And A here is going to be equal to 1. B is going to be equal to the trace, or the negative trace, and then C is going to be equal to this value D, right? So when we set up the quadratic formula, it's going to be rho is going to be equal to 1/2, right, times the trace plus or minus the square root of the trace squared minus 4 times the determinant. All right. Okay, let's give this a whirl with an actual matrix. So let's use the matrix we've been using before. I think we're familiar with this one. So let's say A is equal to the matrix 2, 4, 2, 1, 4, 3. All right. Let's go ahead and plug our values for this into our formula. So here we're going to end up with rho squared minus, so what's the trace is 5, so it's going to be 5 times rho. What's the determinant of this? 6 minus 4 is 2, and that's going to be equal to 0. And let's plug it into our quadratic formula. Rho is equal to 1/2 times 5 plus or minus the square root of 5 squared, which is 25, minus 4 times 2, which is 8. Right? So what's 25 minus 8? This is equal to 17, so this is 1/2 times 5 plus or minus the square root of 17, which tells us the two eigenvalues we have, because we're going to have 2 of them since there's a plus and minus here, is we're going to have rho is equal to 5 plus root 17 over 2 and 5 minus root 17 over 2. Okay? So we can now, all right, so this is essentially how we solve for eigenvalues, right? So we're halfway there. Now we got to refer back to our formula that started this all. All right. So we know what this is, and we're going to have to solve this system out for both of these eigenvalues. So we're going to have 2 eigenvectors. And that's the case. Usually when you have a 2 by 2 matrix, you end up with 2 eigenvalues, 2 eigenvectors. Typically with a 3 by 3 matrix, it'll be 3. And in an n by n, it'll be n eigenvalues and eigenvectors. Right. So let's work on the first one here. Let's try this eigenvalue out first. So if we do that, let's substitute it in. So we have our matrix 2, 4, 1, 3. That's our matrix A, minus our first eigenvalue, which is 5 plus root 17 over 2 times the identity matrix. And we're going to multiply this by our unknown here, v. And we want this to equal 0. Okay? All right, so what is this going to look like? It's going to look like the following. So it's going to be, again, since we're doing the identity matrix, we're going to be subtracting this eigenvalue from each of the elements on the diagonal. So it's going to be 2 minus 5 plus root 17 over 2. And then we have 1 here. And then we're going to have 3 minus root 3 minus 5 plus root 17 over 2. And then we have 4 up here times vector v equals 0. So let's go ahead and try to simplify this out further. So this will be if we try to find a common denominator here, so there's a 2 down here, so how do we turn this into something over 2? This is going to be 4 over 2. Same down here, all right? This is going to be over 2. How do we turn this value into something over 2? It's going to be 6 over 2. That's equal to 3, all right? So when we go ahead and do that, what we'll end up with is this will be equal to negative 1 plus root 17 over 2. And then we have 4, 1, and then here we're going to have 1 minus root 17 over 2 times some vector v1, I'm sorry, some eigenvector v, which we can just write in the variables, equals the 0 vector, which is just going to be equal to this vector here. Okay. So all we have to do is actually literally multiply this out and use algebra. All right. So when we do multiply that out, we're going to have, sorry, I'm moving over to the side because I'm running out of space here. So it's going to be negative 1 plus root 17 over 2 times v1 plus 4 times v2 is equal to 0. And we've got the second set is going to be v1 plus 1 minus root 17 over 2 times v2 equals 0. All right? So we've got two equations and 2 unknowns we can solve for. All right? So there's a trick to doing this. So let's just concentrate on this eigenvector here because we've got one of these sort of already solved out in a way. So let's set v2 equal to 1. So let v2 equal 1. All right. Then it implies, right, that v1 is going to be equal to the negative of this constant here. So that's going to be root 17 minus 1 over 2. Okay, so this gives us our first eigenvector. All right, so v1 is going to be equal to what we wrote here. So root 17 minus 1 over 2 and the number 1. And let's do the exact same steps now for the second. All right. So this eigenvector corresponds to this eigenvalue. These come in a pair. We want to now do this one here. Okay. So again, like I said, we're going to take the exact same steps as before. So let's set up our matrix. So it'll be, again, we'll have 2, 4, 1, 3, that matrix A, minus, now we're going to use this eigenvalue here. So it's going to be 5 minus root 17 over 2 times the identity matrix times V2, you can leave it as V if we want, is equal to 0. So let's go ahead and simplify this out. So again, we're going to have 2 minus 5 minus root 17 over 2 and 4, and then 1, and then 3 minus 5 minus root 17 over 2. All right, it's going to be this matrix times V1, V2 equals 0 and 0. Okay. All right, let me do this over here. So when we simplify this one out, we're going to have the following. It's going to be simplified to root 17 minus 1 over 2, and then 4, and then 1, and root 17 plus 1 over 2 times, again, V1, V2 equals the 0 vector, or the origin. All right. Let's go ahead and factor this out. So when we do that, we get root 17 minus 1 over 2 times V1 plus 4 times V2 equals 0. And we have V1 plus root 17 plus 1 over 2 times V2 equals 0. And we're going to do our same trick. We have this isolated vector element here, V1. Let's just try to solve for that. So let's set V2 equal to the number 1. So again, let V2 equal 1, and then that tells us that V1 is going to be equal to negative root 17 plus 1 over 2, or it'll just be negative. We could leave it as that. That's fine. So then we'll have the following. So eigenvector V2 is going to be equal to negative root 17 plus 1 over 2 and 1. All right. So to summarize, we're going to have the following set of eigenvalues. So summary. We're going to have rho is going to be equal to 5 plus root 17 over 2 and 5 minus root 17 over 2. And it corresponds, so we can actually call this row 1, call this row 2, and then we have V1, or eigenvector 1, is root 17 minus 1 over 2 and 1, and eigenvector 2 is negative root 17 plus 1 over 2 and 1. Right? And again, don't forget the intuition of what we're doing here. The idea here is we've got a 2 by 2 case, and we're looking for some, and there's going to be two of them. There's going to be two sets of these. A scalar row and a vector v that take, that are invariant to multiplication by this matrix A, and in fact send the directions back into the origin. All right. So again, pretty powerful stuff. All right, I'm going to end the video there, and the next video is going to go over the 3 by 3 case. I know you're all excited for that.